Hi, my name is Rutuj Waghare, and our topic for research survey is Imbalance Data Methodologies. My group members are Ritika, Sinha, and Kumar, Anubhav. Now, before talking about the methodologies and their comparison, let's try to understand the problem statement. Suppose that you are working in a given company and you are asked to create a model that, based on various measurements at your disposal, predicts whether the product is defective or not. You decide to use your favorite classifier, train it on the data, and deploy it. You get 96% accuracy. Your boss is astonished and decides to use your model without any further test. A few weeks later, he enters your office and underlines the uselessness of your model. Indeed, the model you created has not found any defective product from the time it has been used in production. After some investigation, you find out that there is only around 4% of the product made by your company that are defective, and your model just always answers not defective, leading to a 96% accuracy. The kind of naive results you obtained is due to the imbalanced dataset you are working with. There are several aspects that might influence the performance achieved by the existing learning system. It has been reported that one of these aspects is related to the class imbalance, in which examples in training data belonging to one class heavily outnumbers the examples in the other class. This sort of data is found, for example, in medical record database regarding a rare disease, where there is a large number of patients who do not have that disease. Another example is a continuous fault monitoring task, where non-faulty examples heavily outnumber the faulty examples. Now, to understand it better, let's consider one example. Let's suppose that we have two classes, C0 and C1. Points from class C0 follow a one-dimensional Gaussian distribution of mean 0 and variance 4. Points from the class C1 also follow a one-dimensional Gaussian distribution of mean 2 and variance 1. Suppose also that in our problem, the class C0 represent 90% of the data set, and so the class C1 represent the remaining 10%. In the following picture, we have depicted a representative data set containing 50 points along with the theoretical distribution of both classes in right proportion. In this example, we can see that the curve of C0 class is always above the curve of C1 class, and so for any given point, the probability that this point was drawn from the class C0 is always greater than the probability it was drawn from class C1. Mathematically, using Bayes rule, we can write this as P0 given X, and accordingly this. Here we can clearly see the effect of prior and how it can lead to a situation where a class is always more likely than the other. All this implies that even from a perfect theoretical point of view, we know that if we had to train a classifier of this data, the accuracy of the classifier would be maximal when always answering C0. So if the goal is to train a classifier to get the best possible accuracy, then it should not be seen as a problem, but just as a fact. With these features, the best we can do is to always answer C0. Next, we will talk about the separability. So in the given example, which I just mentioned, we can observe that the two classes are not well separable. They are not far apart from each other. However, we can notice that facing an imbalanced data set doesn't necessarily mean that two classes are not well separable, and so that the classifier can't do a pretty good job on the minority class. For example, consider that we still have two classes, C0 and C1. Data in C0 follow a one-dimensional Gaussian distribution of mean 0 and the variance 4, whereas data in C1 follow a one-dimensional Gaussian distribution of mean 10 and variance 1. So if we plot the data as before, we then have this kind of graph. Here we see that contrarily to the previous case, the C0 curve is not always above the C1 curve, and so there are points that are more likely to be drawn from class C1 than from class C0. In this case, two classes are separated enough to compensate the imbalance. Classifier will not necessarily answer C0 all the time. Hence, the traditional modeling algorithms do not always perform well on the imbalanced data, and so the class imbalance methodologies are proposed to improve the prediction performance of modeling algorithms. So we have discussed the techniques that deal with the data imbalance in the training data, and we noted that the evaluation of model performance is based on testing data. In this section, we review the common performance measures and their appropriateness to imbalance data. The most straightforward way to evaluate the performance of classifier is based on the confusion matrix analysis. From such matrix, it is possible to extract a number of widely used metrics for measuring performance of learning systems such as error rate, accuracy, misclassification rate, precision and recall, etc. Accuracy is a measure of overall efficiency of a model. However, the accuracy may not be appropriate when the data is imbalanced. In that case, more weights are placed on the majority class than on the minority class, and the model may not perform well on the minority class even with a high accuracy. To accommodate the cost of minority class, receiver operating characteristic curve is proposed as a measure over a range of trade-off between the true positive rate and false positive rate. ROC graphs are consistent for the given problem, even if the distribution of positive and negative example is highly skewed. Another metric is area under the curve, which is AUC. It is commonly used for performance metric for summarizing the ROC curve in a single score. Moreover, AUC is not biased towards model performance on the majority or minority class, which makes this measure more appropriate when dealing with the imbalanced data. From the confusion matrix, we can also derive precision and recall performance metric, which are defined as precision equals to true positive upon true positive plus false positive, and recall, which is defined as true positive upon true positive plus false negative. The precision of a class defines how trustable is the result when the model answer that a point belongs to that class. The recall of a class expresses how well the model is able to detect the class. For imbalanced data, the main goal is to improve the true positive for the minority class. However, the number of false positive can also increase in that case. To balance the recall and precision, that is improving the recall while keeping precision low, the F score is proposed as a harmonic mean of precision and recall. F score is defined as 2 into precision into recall upon precision plus recall. Since the F score weights precision and recall equally and balances both concerns, it is less likely to be biased to the majority or minority class. To handle the class imbalance problem, we have few methods available like sampling methods, ensemble methods, and cost-sensitive methods. We will be discussing some of these methods in upcoming slides.
Hi, my name is Kumar Anubhav and I am from MTech Mathematics and Computing Department. I will be explaining about the methodologies that we have used in our survey. So I will explain what is sampling method and why we are using it. So sampling method is a technique that applies at the data level for balancing the majority and minority classes. So the question arises here that what is majority class and what is minority class? So let's get clear with an example. So consider a data set that contain two classes. So we can say here that the class that is present in a very large number in the data set is known as majority class, and the class that is present in very less number in the data set is known as minority class. So basically this method works at the data pre-processing step, either by oversampling the minority class or by undersampling the majority class. So basically we do this type of things to construct a well-balanced training data set. So what are the types of the sampling methods? So basically there are two types of sampling methods. So the first one is random undersampling. So it is a non-heuristic method that aims to balance the class distribution through the random elimination of majority class example. So in the given figure, we can also see that the orange one is representing the minority class and the blue one is representing the majority class. And here we are trying to remove or eliminate the majority class so that it get equal to the number of minority class. So several methods have been proposed here so that the information of the majority class would be largely retained in the training data set. Now the next one is random oversampling methods. So in the random oversampling methods, it is also non-heuristic methods that aims to balance class distribution through the random replication of the minority class example. So in the figure, we can also see that the orange color here is representing a minority class and we are trying to replicate and get it equal to the number of majority class. So information of the majority class here is fully retained, but the duplicacy of the minority samples leads the modeling algorithm to be trained on more specific regions, or it could also lead to overfitting problems. So the next one is CNN. So what is CNN? So CNN is basically a undersampling methods that stands for condensed nearest neighbor, and it was proposed by Hart in 1968. So this methods only removes majority samples far away from the decision neighbors, and it is an iterative type of approach because CNN rule is repeated on the training data set until the set to be removed is stable. So in the given figure, we can also see that the orange color is representing class 1, and while blue color is representing class 0, and the green color is representing class removed samples. So here in each iteration, each of the majority class has been removed because as far because they are far from the decision neighbor. And we can also say here that here only safe majority class examples and all the minority class examples are used for learning purpose. Now the second one is ENN. So what is ENN and why we are using it? So ENN is also a undersampling methods, or we can say it stands for edited nearest neighbor rule. So it was proposed by Wilson in 1972. So this method uses nearest neighbor for removing samples that do not agree with the majority of its k nearest neighbors. So basically this algorithm edits out the samples that are identified as noise or borderline and leaves smoother boundaries. We can also see it from figure here. So the next one is Tomic links. So what is Tomic links and why we are using it? So it is also another type of undersampling approach, and it was proposed by Tomek in 1976. So it is another approach such that only majority samples identified on as Tomek links are removed. So here we can see that the samples of majority, or we can say the samples of the majority class, are only removed if and only if they are identified as the Tomek links. So what is Tomek links? First I will try to explain it. So consider the 2 points EI and EJ. So EI and EJ is said to be Tomek links if there is not any point EL such that the distance between EI and EL less than EI and EJ. So by checking the Tomek links between the nearest neighbors pairs, majority samples are removed until all the minimal distance nearest neighbor pairs are in the same class. Now the next one is SMOOT. So SMOOT is a oversampling technique, and it stands for synthetic minority oversampling technique and was proposed by Chawla et al. In 2002. So here circle representing minority class and the triangle is representing the majority class. So it generates synthetic samples for minority class based on their nearest neighbors to shift the learning bias towards the minority class. We can also see it in the figure here, like the circle is representing the minority class, and we have generated here synthesized data, or we can say synthetic samples by, based on their nearest neighbors to shift the learning bias towards the minority class. So this algorithm chooses nearest neighbor by Euclidean distance between the data points and generates the synthetic samples by taking a linear we can say by taking a linear segment between the same under consideration and its nearest neighbor. So the next one is SMOOT plus Tomic links. So we have already seen each of these SMOOT as well as Tomic links. So the SMOOT is a oversampling type of method, while the Tomic links was a undersampling type of method. So collectively we can say that if both are merged and proposed as a single method, then we can say it is a type of hybrid method. So in the given problem, in the given figure, we will try to identify that what is happening here. So in the figure A, we can say that it is a oversampled data sets, and in the figure B, we are trying to identify the Tomic links, and in the figure C, we can say that we are trying to identify borderlines and examples, and in the figure 4 or D, we can finally say that we are finally cleaning the uh, data set and trying to prepare our training data set. The next one is SMOOT plus ENN. So as we can see that it is also a type of hybrid method, as SMOOT is the oversampling method while ENN is the undersampling method. So in the first stage, SMOOT process has been happened, while in the next stage ENN has been happened. So Here we can say that the green color is representing the majority class, while the light yellow color is representing the minority class, and the dark yellow is representing the smooth samples, and the red color is representing the removed samples. So in the first process, smooth or we can say synthetic data has been generated based on the minority class on according to their nearest neighbor or the Euclidean distance property. We can say that we have studied in the smooth. In the second part, the ENN method has been done here, so it will try to remove the some samples from the majority class according to their ENN property, or we can say according to the ENN rule. So finally, we are at the stage of conclusion, and I would like to conclude the sampling method here. So we can say that both oversampling and undersampling techniques can be effective when used in isolation, but the combination of both the technique could be more effective for imbalanced data sets here. So SMOT plus stomach links we have already seen in the last slide, and SMOT plus CNN we have also seen this example are. So we can say that both of these methods that has been proposed are addresses the concern of overfitting introduced by artificial minority samples. So the first SMOT algorithm is applied to the original data set to oversample the minority samples. Then minority samples in atomic links are identified and removed, or the misclassified majority samples by its nearest neighbor is removed by the ENN rule. So we can use any undersampling methods for removing the majority class based on our needs. And finally, we can say that the hybrid algorithms have been showed good experiment results when compared to the oversampling methods alone. So this is the whole sampling method that I've tried to explain.
Hello, Ritika. I will be explaining about two more popular methodologies for handling data imbalance, which are ensemble classifiers and cost-sensitive. So before getting started, let us see what ensemble learning is. Unity is strength. This old saying expresses pretty well the underlying idea that rules the very powerful ensemble methods in machine learning. Ensemble learning combines several base algorithms to form one optimized predictive algorithm. It is a machine learning paradigm where multiple models, often called weak learners, are trained to solve the same problem and combined to get better results. The main hypothesis is that when the weak models are correctly combined, we can obtain more accurate or robust. In machine learning, no matter if we are facing a classification or a regression problem, the choice of the model is extremely important to have any chance to obtain good results. This choice can depend on many variables of the problem: quantity of data, dimensionality of the space, distribution hypothesis, and so on. A low bias and a low variance, although they most often vary in opposite directions, are the two most fundamental features expected for a model. Indeed, to be able to solve a problem, we want our model to have enough degrees of freedom to resolve the underlying complexity of the data we are working with. But we also want it to have not too many degrees of freedom to avoid high variance and be more robust. This is the well-known bias variance trade. Now, as we can see in this illustration, bias is a decreasing function, whereas variance is an increasing function. The optimal balance is obtained when the two lines cut each other. The test error is also minimum in this case. If we try to minimize the variance, we may end up in the underfitting zone as the bias increases. Similarly, if we try to minimize the bias, the model tends to overfit as the variance increases. Now, we need to combine the weak learners. In order to set up an ensemble learning method, we first need to select our base models to be aggregated. Most of the time, including in the well-known bagging and boosting methods, a single base learning algorithm is used so that we have homogeneous weak learners that are trained in different ways. The ensemble model we obtain is said to be homogeneous. However, there also exist some methods that use different type of base learning algorithms. Some heterogeneous weak learners are then combined into heterogeneous ensemble models. One important point is that our choice of weak learners should be coherent with the way we aggregate these models. If we choose base models with low bias but high variance, it should be an aggregating method that tends to reduce variance, whereas if we choose base models with low variance but high bias, it should be with an aggregating method that tends to reduce bias. Now, this brings us to the question of how to combine these models. We can mention three major kinds of meta algorithms that aim at combining weak learners. Bagging, that often considers homogeneous weak learners, learns them independently from each other in parallel and combines them following some kind of deterministic averaging process. Boosting, that often considers homogeneous weak learners, learns them sequentially in a very adaptive way. A base model depends on the previous ones and combines them following a deterministic strategy. Stacking, that often considers heterogeneous weak learners, learns them in parallel and combines them by training a meta model to output a prediction based on the different weak models' predictions. Very roughly, we can say that bagging will mainly focus at getting an ensemble model with less variance than its components, whereas boosting and stacking will mainly try to produce strong models less biased than their components, even if variance can also be reduced. Now we will focus on boosting. In boosting, we try to fit multiple weak learners sequentially in a very adaptive way. Each model in the sequence is fitted, giving more importance to observations in the dataset that were badly handled by the previous models in the sequence. Intuitively, each new model focuses its efforts on the most difficult observations to fit up to now, so that we obtain, at the end of the process, a strong learner with lower bias, even if we can notice that boosting can have the effect of reducing variance. Boosting can be used for regression as well as classification problems. Being mostly focused at reducing bias, the base models that are often considered for boosting are models with low variance but high bias. For example, if we want to use trees as our base models, we will choose most of the time shallow decision trees with very low depth. Another important reason that motivates the use of low variance but high bias models as weak learners for boosting is that these models are in general less computationally expensive to fit, only few degrees of freedom when parameterized. Indeed, as computations to fit the different models can't be done in parallel, it could become too expensive to fit sequentially several complex models. Once the weak learners have been chosen, we still need to define how they will be sequentially fitted and how they will be aggregated. We will now discuss this in the upcoming part with the help of an important boosting algorithm known as AdaBoost. AdaBoost, which is short for adaptive boosting, is a very popular boosting technique that aims at combining multiple weak classifiers to build one strong classifier. The original AdaBoost paper was authored by Freund and Shafire. Rather than being a model in itself, AdaBoost can be applied on top of any classifier to learn from its shortcomings and propose a more accurate model. It is usually called the best out-of-the-box classifier for this reason. Now, let us try to understand how AdaBoost works with the help of decision stumps. Decision stumps are like trees in a random forest, but not fully grown. They have one root node and two leaves. AdaBoost uses a forest of such stumps rather than trees. Stumps alone are not a good way to make decisions. A full-grown tree combines the decisions from all the variables to predict the target value. A stump, on the other hand, can only use one variable to make a decision. Now let's see the algorithm for ADA boost. Step 1. A weak classifier, for example, a decision stump, is made on top of the training data based on the weighted samples. Here the weights of each sample indicate how important it is to be correctly classified. Initially, for all the samples, we give all the samples equal weights. Step 2. We create a decision stump for each variable and see how well each stump classifies samples to their target classes. We look at how many samples are correctly or incorrectly classified. Step 3. More weight is assigned to the incorrectly classified samples so that they are classified correctly in the next decision stump. Weight is also assigned to each classifier based on the accuracy of the classifier, which means that high accuracy equal to high weight. Step 4. We reiterate from step 2 until all the data points have been correctly classified or the maximum iteration level has been reached. Now we will try to understand the mathematics behind ADA boost. Let's break ADA boost down step by step and equation by equation so that it's easier to comprehend. We start by considering a data set with capital N points or rows in our data set. Xi belongs to capital R raised to the power small n, yi belongs to minus 1, 1. In this case, n is the dimension of real numbers or the number of attributes in our data set. X is the set of data points and y is the target variable, which is either minus 1 or 1, as it is a binary classification problem. Now we calculate the weighted samples for each data point. ADA boost assigns weight to each training example to determine its significance in the training data set. When the assigned weights are high, that set of training data points are likely to have a larger say in the training set. Similarly, when the assigned weights are low, they have a minimal influence in the training data set. Initially, all the data points will have same weighted sample W. W equal to 1 by n belongs to 0, 1, where capital N is the number of data points. The weighted samples always sum to 1, so the value of each individual weight will always lie between 0 and 1. After this, we calculate the actual influence for this classifier in classifying the data points using the formula alpha t equal to half ln 1 minus total error by total error. Alpha is how much influence this stump will have in the final classification. Total error is nothing but the total number of misclassifications for that training set divided by the training set size. We can plot a graph for alpha by plugging in various values of total error ranging from 0 to 1. Notice that when a decision stump does well or has no misclassifications, this results in an error rate of 0 and a relatively large positive alpha value. If the stump just classifies half correctly and half incorrectly, that is an error rate of 0.5, no better than random guessing, then the alpha value will be 0. Finally, when the stump ceaselessly classifies results in the wrong way, then the value of alpha would be a large negative value. Now, after plugging in the actual values of total error for each stump, it's time for us to update the sample weights, which we had initially taken as 1 by n for every data point. We'll do this using the following formula. Wi equal to Wi into e to the power plus minus alpha. In other words, the new sample weight will be equal to the old sample weight multiplied by Euler's number raised to plus or minus alpha, which we just calculated in the previous step. There are two cases for alpha. positive or negative. Alpha is positive when the predicted and the actual output agree. The sample was classified correctly. In this case, we decrease the sample weight from what it was before, since it was already performing well. Alpha is negative when the predicted output does not agree with the actual class, that is, the sample is misclassified. In this case, we need to increase the sample weight so that the same misclassification does not repeat in the next term. This is how the stumps are dependent on their predecessors. With this, we complete the explanation of ADA boost. Now let us focus on bagging. Bagging, also known as bootstrap aggregation, is the ensemble technique used by random forest. Bagging chooses a random sample from the dataset. Hence, each model is generated from the samples provided by the original data with replacement known as row sampling. This step of row sampling with replacement is known as bootstrap. Now, each model is trained independently which generates results. The final output is based on majority voting after combining the results of all models. This step, which involves combining all the results and generating output based on majority voting, is known as aggregation. Now let's see the steps involved in random forest algorithm. Step 1. In random forest, n number of random records are taken from the dataset containing k records. Step 2. Individual decision trees are constructed for each sample. Step 3. Each decision tree generates an output. Step 4. Final output is considered based on majority voting or averaging for classification and regression respectively. Now, let us take for example this food basket as the given data. Now, n number of samples are taken from the food basket and an individual decision tree is constructed for each sample. Each decision tree will generate an output as shown in the figure. The final output is considered based on majority voting. In this figure, we can see that the majority decision tree gives output as an apple when compared to a banana. So the final output is taken as an apple. Now let's see some important features of random forest. Number 1 is diversity. Not all attributes or variables are considered while making an individual tree. Each tree is different. Number 2, immune to the curse of dimensionality. Since each tree does not consider all the features, the feature space is reduced. Number 3, parallelization. Each tree is created independently out of different data and attributes. This means that we can make full use of the CPU to build random forests. Number 4, train test split. In a random forest, we don't have to segregate the data for train and test as there will always be 30% of the data which is not seen by the decision tree. Number 5, stability. Stability arises because the result is based on majority voting or averaging. However, similar to most classifiers, random forests can also suffer from the curse of learning from an extremely imbalanced training data set. As it is constructed to minimize the overall error rate, it will tend to focus more on the prediction accuracy of the majority class, which often results in poor accuracy for the minority class. To alleviate the problem, we propose two solutions: balanced random forest (BRF) and weighted random forest (WRF). Now we will look at balanced random forest, which is another ensemble classifier like ADA boost. Random forest induces each constituent tree from a bootstrap sample of the training data. In learning extremely imbalanced data, there is a significant probability that a bootstrap sample contains few or even none of the minority class, resulting in a tree with poor performance for predicting the minority class. A naive way of fixing this problem is to use a stratified bootstrap, that is, sample with replacement from within each class. This still does not solve the imbalance problem entirely. As recent research shows, For the tree classifier, artificially making class priors equal either by downsampling the majority class or oversampling the minority class is usually more effective with respect to a given performance measurement, and that downsampling seems to have an edge over oversampling. However, downsampling the majority class may result in loss of information as a large part of the majority class is not used. Random forest inspired us to ensemble trees induced from balanced downsampled data. The balanced random forest algorithm is shown below. For each iteration in the random forest, draw a bootstrap sample from the minority class. Randomly draw the same number of cases with replacement from the majority class. Next, induce a classification tree from the data to maximum size without pruning. The tree is induced with the cart algorithm. The following modification: at each node, instead of searching through all variables for the optimal split, only search through a set of m-try randomly selected variables. Lastly, repeat the two steps above for the number of times desired. Aggregate the predictions of the ensemble and make the final prediction. Next, let's see weighted random forest, which is a cost-sensitive approach. In this, we assign a weight to each class, with the minority class given larger weight, that is higher misclassification cost. The class weights are incorporated into the random forest algorithm in two places. In the tree induction procedure, class weights are used to weigh the Gini criterion for finding splits. In the terminal nodes of each tree, class weights are again taken into consideration. The class prediction of each terminal node is determined by weighted majority vote. That is, the weighted vote of a class is the weight for that class times the number of cases for that class at the terminal node. The final class prediction for random forest is then determined by aggregating the weighted vote from each individual tree, where the weights are average weights in the terminal nodes. Class weights are an essential tuning parameter to achieve desired performance. The out-of-bag estimate of the accuracy from random forest can be used to select weights.
So in previous section, we have discussed the performance measure like precision, recall, F-score, and ROC. In this section, we will talk about the comparison of class imbalance method. For comparing the class imbalance method, we are considering the results proposed by one of the research paper. The test is performed on 15 datasets. So as you can see it in table, it consists of size, majority and minority class data, ratio between them, data source, and original data size. They randomly downsample the minority samples to achieve a higher imbalance ratio for some datasets. The model performance is measured by F-score and AUC on testing datasets. The whole testing process is repeated for 50 times, and the performance values are averaged over the 50 iterations for each dataset. The final performance value at algorithm level is the averaged F-score or AUC over the 15 experimental datasets. Here we will compare the performance of 8 algorithms, which include logistic regression, linear support vector classifier, nearest neighbor, classification and regression trees, random forest, gradient boosting tree, undersampling with AdaBoost, and easy ensemble. For each modeling algorithm, the models are built on the original training dataset as the baseline and on the training datasets after applying imbalance methods for comparison. We test 4 classed imbalance method, that is SMOT, adaptive synthetic sampling, that is ADASYN, SMOT ANN, and SMOT TOMAC. The hyperparameter for this modeling algorithm are tuned by grid search so that F-score, AUC, and accuracy metrics on training datasets are optimized. So given table shows the impact of imbalance methods across the modeling algorithm categories. So first one is for linear algorithm, logistic regression, and linear SVC. The model performance measured by AUC improves after applying the imbalance method to the training dataset. With any of the class imbalance method, the AUC improves significantly from 85.08% to 87% for logistic regression, and from 83.33% to 86% for linear SVC. The F-score is not very sensitive to the imbalance method, where the values are comparable with the original baseline for SMART method and drop slightly for adaptive synthetic method. Overall, both linear algorithm perform better with the imbalance method, and it is recommended to pre-process the dataset before training the model. For simple nonlinear algorithm, nearest neighbor and cart, the performance results are mixing and we do not observe consistent improvement. For nearest neighbor, the AUC improves from 80.79% to 83% for most of the imbalance method, except only 0.02% improvement for SMART ENN. For CART, the AUC is the highest when the model is trained on the original dataset and decreases slightly after applying the imbalance method. When measured by F-score, the performance drops significantly from original 69.09% to 50 to 65% for nearest neighbor, and from 64.69% to 55 to 61% for CART. Specifically with SMART ENN, the F-score drops to 50.57% for nearest neighbor and 55.30% for CART. Since the nearest neighbor algorithm is mostly used to classify the new data point based on how its neighbors are classified, the decision boundary is sensitive to the sample composition. CART has the well-known weakness of non-robustness, and a small change in training data can result in large change in the tree and consequently the final predictions. Therefore, both algorithms are more likely to be overfitted when the minority class is oversampled and the performance on the more imbalanced testing dataset drops. For ensemble algorithm, that is random forest and XGBoost, the improvement of model performance is also not obvious after applying imbalance method. For both algorithms, the AUC with or without imbalance method are around 89% with few variations. The F-score for random forest decreases from the baseline 70.90% to 67 to 69% when pre-processed by imbalance method, but for XGBoost, the values are almost the same. Since the ensemble algorithm already performed well on the imbalance dataset, the impact of imbalance method are not significant. The RUSB and the easy ensemble are ensemble algorithms that could handle data imbalance, where the ADA boost model is trained iteratively on balanced sample with oversampling or undersampling. Since these two algorithms are already rebalanced the data in the training process, the additional imbalance method in the data preprocessing step will not contribute further improvement to algorithm performance. For AUC, both algorithms perform best when trained on the original dataset. For F-score, we observe less than 1% improvement for RUSB and slightly worse value for easy ensemble. The second set of comparison is conducted between the modeling algorithms on imbalanced dataset. Still, the results are biased on the grid search with AUC. For linear algorithms and simple nonlinear algorithm, the AUC is greatly lower than the more complex algorithm like ensemble algorithm and the imbalance algorithm. The simpler algorithm tend to have better model interpretability than the more complex algorithm with sacrificing on performance. Specifically, the more complex algorithm combine the decision from multiple model iterations and improve the overall model performance even with the data imbalance. The simple nonlinear algorithm perform worst among all algorithm categories in AUC, and we would not recommend choosing this algorithm for the imbalanced datasets. When measured by F-score, the ensemble algorithm, that is random forest and XGBoost, outperform other algorithm categories. It is showed that with similar AUCs, the ensemble algorithm achieves slightly better F-score than imbalance algorithm. Therefore, even without imbalance method, the ensemble algorithm still works well for imbalanced dataset. Lastly, we compare the performance between grid search criteria. All 8 modeling algorithms are tuned by grid search with AUC and F-score as criteria, and RUSB and easy ensemble could not be tuned by accuracy. The results are very close for different grid search criteria. Since the performance is measured by AUC and F-score, when hyperparameters are tuned by AUC, the algorithm performs better than the other grid search criteria for the corresponding performance measurement. However, F-score is not consistently better when tuned by F-score. The simple nonlinear algorithm, that is nearest neighbor and the cart, are more sensitive and grid search criteria to the grid search criteria. The more complex ensemble and the imbalance algorithm are less sensitive and achieve high AUC and F score for all three grid search criteria. So this was all about the comparison of different balancing methodologies.
With this, we come to the conclusion. In this presentation, we provided an overview of different methodologies used to deal with imbalanced data. In the past 20 years, so many methodologies were developed to deal with this problem. It becomes difficult to choose the right imbalance methods in a real-world problem. Our empirical study compared the performance of some typical imbalance methods on large number of real data sets. We also studied the interactions between class imbalance methods and modeling algorithms. We found that imbalance methods do not always have consistent improvements. Their improvements depend on the modeling algorithm used. The imbalance methods are most suitable for simple linear algorithms. We also observed that different imbalance methods do not have significant different behaviors. Using more complicated ensemble modeling algorithms will achieve best performance on imbalanced data, even without applying imbalance methods. AUC or F score is the main objective of the model. We recommend to use more complicated ensemble modeling algorithms without imbalance methods. If model interpretation is also a key objective, we recommend to use linear algorithms combined with any of the imbalance methods studied in this presentation. So with this, we end this presentation. Thank you for watching the video and have a good day.